So welcome to the second lecture on functional programming. Before I forget it, on Wednesday there will also be a lecture instead of the exercise course. So on Wednesday there will be lecture instead of exercise course. Okay, so 3 lectures this week. Now what did we do in the last lecture? We introduced Haskell and we started with a very simple example program which simply takes an integer number and squares it. And such a Haskell program typically consists of 2 parts if we want to introduce a new function, the type declaration and the function declaration. So the type declaration would look like this. We would say that square is a new variable and the variable has the type int arrow int, which means that it's a function that maps integers to integers. And here's the function declaration saying how square actually works. So square takes an argument that looks like this, some x, and it returns x times x. So formally, we introduced this by some grammar rules which describe how to construct these type declarations and how to construct these function declarations. So a Haskell program is just a sequence of declarations, and every declaration is either a type declaration or a function declaration. Type declarations look like this. They introduce a certain number of variables. In our example, it's just a single variable. Then we have a double colon, and then we tell Haskell which is the type of this new variable. So in our example, the type is int arrow int. Now, what is a variable? A variable syntactically is just a string that starts with a lowercase symbol. We will have strings starting with uppercase symbols later on, and they mean something else. Okay, then what are function declarations? Well, function declarations consist of a function left-hand side and a right-hand side. The function left-hand side, well, that's the part that is left of the equality sign. So it's the variable, the name of the function, and a pattern. And a pattern is a special expression that describes the form of expected arguments. In our example, the pattern is x, and that describes that we can use any argument here. So any integer is allowed here. And the right-hand side consists of an equality sign and some expression, for example, this expression over here, which is built from the variable x and the predefined operation times. Okay, so this is what we had in the last lecture. So you can type this in and save this in some file called square.hs for Haskell, and then you can try to execute this program. So you can start your favorite Haskell compiler or interpreter, and our favorite Haskell compiler or interpreter is GHC, the Glasgow Haskell compiler in its interactive mode. And well, there are certain commands here, and the commands in this Haskell interpreter or Haskell compiler, they start with a colon. So for example, :L means load. So if I load this file, if I say load square HS, well, then it loads this file. And now Haskell knows not only the predefined operations, but also the operation square that we defined ourselves. And then afterwards, you can type in things like square of 12 minus 1. And then again, you press return. And well, minus is predefined, so Haskell knows how to execute minus. And square is not predefined, but we defined it ourselves. And we told Haskell, load this file. And so it can also evaluate square. And of course, this interpreter has many other commands. And if you want to know more, you can type in :H for help. And then you get a description of all the commands that are available. And there's a manual and a tutorial, so you can play around with it. Now what happens if you type in square of 12 minus 1? It's not completely clear how to evaluate an expression like this, because you could start here and start evaluating minus, or you could start here and start evaluating 12. So to look at all the possible evaluation sequences, I prepared this slide. And the slide describes what we can do if we want to evaluate 12 of square of 12 minus 1. So one possibility is to start with the evaluation of minus. So then we first evaluate this argument, and 12 minus 1 evaluates to 11. So then we get from this expression to this expression. And now square 11 to evaluate this. Well, Haskell looks at the defining equations, and it performs term rewriting. So it looks for some sub-expression over there such that the left-hand side of this equation matches the sub-expression. And indeed, if we instantiate this variable x by 11, then we have square 11 here, and this matches exactly this expression. So this corresponds to the left-hand side of this equation, and therefore we can rewrite this expression to the corresponding right-hand side. And the right-hand side is x times x, but x is instantiated by 11, so the right-hand side is 11 times 11. And now 11 times 11 can again be evaluated because times is predefined, and Haskell reaches the result 121. So this is one possibility. We could evaluate it like this. And this evaluation strategy, which I marked here in red, is called Innermost Evaluation strategy because, well, if we have the choice to evaluate something which is at the more inside position like minus and something which is more at the outside position like square, then the innermost strategy would decide to evaluate the innermost functions first. So it would first evaluate arguments and then apply the functions to these arguments. But we could do it also in a different way. We could say, well, let's not evaluate minus, but let's evaluate square. Now that's also possible because to apply this equation, well, the only thing we have to do is we have to instantiate this variable in such a way that the left-hand side corresponds to the expression that we want to evaluate. So why don't we instantiate x by the expression 12 minus 1, the non-evaluated expression 12 minus 1? If we do that, then indeed here we have square of 12 minus 1, and this can be rewritten to 12 minus 1 times 12 minus 1. And this is what happens here. So we could also evaluate square directly, and then we reach this expression, 12 minus 1 times 12 minus 1. So we can really apply functions to expressions that are not yet evaluated. Now, how would we proceed further? There are three operations here, minus, times, and minus. Now, the times we cannot evaluate because times only works if both arguments are already numbers, really numbers that are completely evaluated. But we could evaluate this minus, and we could evaluate this minus. So if we evaluate this minus, well, then this sub-expression becomes 11. So we have 11 times 12 minus 1. And if we evaluate the other minus, then we reach, well, 12 minus 1 times 11. So this is possible. And then if we continue evaluating, in the next step here, we would have to evaluate 12 minus 1 to 11. And here we would have to evaluate 12 minus 1 to 11. So in all cases, we reach 11 times 11, which is then evaluated to 121. So there are three possible paths through this graph. And well, at this point, these two minuses, they are equally inside or equally outside. And then typically, one decides to evaluate the leftmost function before evaluating the rightmost function. And so this strategy, which is depicted in green here, is called leftmost outermost. So we always try to evaluate as outermost as possible. And if there are choices between two function symbols which are equally outermost, then we take the leftmost one. So these are two typical strategies, leftmost innermost and leftmost outermost. And now the question is, what does Haskell do? So maybe we first answer the question, what does your favorite imperative programming language do? So if you think of Java or C or whatever imperative language you like, what is the strategy used by imperative languages? Did you ever type something like this in an imperative language, square of 12 minus 1? Yeah, of course you can type this. And then what happens? Will it first evaluate square, or will it first evaluate minus? Yeah, minus, right. So all the imperative languages, they do leftmost, innermost. And many functional languages do that too, but not Haskell. Haskell does indeed something like leftmost, outermost. So this leftmost, innermost evaluation this is also sometimes called eager evaluation, because as soon as the the computer finds something that it can evaluate, it starts evaluating. So it's very, very eager, and it wants to evaluate whenever possible. So it's an eager or strict evaluation. So this is done in Java or C or whatever. So it's done in most languages. But the alternative is leftmost, outermost. And, well, which is also called non-strict evaluation. And, well, now we can discuss what are the advantages and disadvantages of these two evaluation strategies. So, well, first thing is that luckily they reach the same result. So no matter what evaluation strategy you use, it ends up with 121. And the first question is this coincidence, or are there programs where with this one strategy you get 121 and with the other you get 122? So it's pure chance what your result is. Well, luckily this is not the case. So what are the observations on these strategies? So if two evaluations terminate for the same expression, if two evaluations of the same expression terminate, then they reach the same result. So in that sense, it doesn't really matter what evaluation strategy you use. The result is the same. But sometimes it does matter because the evaluation strategy might influence the efficiency of your computation, and it might also influence the termination behavior of your computation. So, but the evaluation strategy can influence the efficiency and the termination behavior. And to make that clear, let's look at an example. So suppose we have the following two functions in Haskell. One function is called 3, and that's a very boring function because it takes an integer, but it returns 3. So it just ignores its argument. So 3 of x is the number 3. So no matter to which number you apply this thing, it always returns 3. And we have another Haskell function which is called non-term because it computes something which is non-terminating. So non-term is also a function from int to int. And it works like this. If I call non-term with x, then non-term calls itself recursively with x plus 1. Okay, that looks rather dangerous. If you want to compute non-term of 0, then you will try to compute non-term of 1. And to compute this, you get non-term of 2, non-term of 3, and so on. So this looks pretty non-terminating. Okay, now what happens with the following expression? 3 of non-term 0. What's the result of this? This depends on the strategy. So if you decide on innermost evaluation, then you will evaluate the argument first. Well, and that will never terminate. So you get non-term 0, non-term 1, and so on. So this will never terminate, and, well, you get no result. So this does not terminate for innermost evaluation. But if you take outermost evaluation, well, then you try to evaluate the function symbol that is at the outermost position. So you try to evaluate 3. And indeed, this is possible because 3 of anything is 3. So you don't have to evaluate non-term. You just apply this rule here, and in one step you get the result. So this is 3 for outermost evaluation. And so indeed, there are examples where outermost evaluation terminates and innermost evaluation does not terminate. So one gets the following result. If any evaluation terminates, then leftmost outermost evaluation terminates as well. So this terminates as often as possible. If any evaluation terminates, then outermost evaluation also terminates. So in that sense, this is the best strategy. So we have seen that as far as termination is concerned, outermost termination is better. I mean, it terminates more often. And, well, with the same example, you can also imagine that outermost termination can be faster, can be more efficient. So, I mean, if you compute something like 3 of f of 0, and f is a function that takes really, really long to compute. So to evaluate f of 0, you take a whole year of evaluation. And now if you do innermost evaluation, you spend 1 year on evaluating f of 0, then you throw the result away and return the number 3. So it's a bit smarter to evaluate 3 first, because then you need 1 evaluation step and you have the result immediately. So let's say this takes, I don't know, thousands evaluation steps. Okay, this should be faster than a year. And then outermost is clearly more efficient than innermost. Than innermost. So this looks as if outermost is always better than innermost, but is that really true? Or can you think of examples where it's the other way around, where innermost is better? Yes?
You use square of this function, and then you need 2,000 steps for outermost.
Yeah, okay, so what happens if I do square of this nasty thing? So how many evaluation steps do I need for outermost? How many do I need for innermost?
Innermost does not change. It's 1,001 steps.
Right?
The outermost, it's 2,001.
Exactly. So, exactly. In fact, the same thing we have already if we do 12 minus 1. So, I mean, there the difference is not so dramatic, but the same thing happens, because you duplicate the argument. So if you count the steps here, we see the same thing. So here, this needs only 1 evaluation step instead of 1,000. The advantage is that I can write it on the slide, but 1,000 arrows would not fit on this transparency. So if I do innermost, how many steps do I need? Well, 1, 2, 3. So 3 steps for innermost. And how many do I need for outermost? Well, 1, 2, 3, 4. 4 steps for outermost. And, well, you might say, well, 3 steps, who cares? But if this takes 1,000 steps, then indeed here we have, I think we have 1,002, because you need 1,000 for those. And then you need 1 step to replace square by this times this, and another step to execute the times. So I would say 1,002 steps if you do it innermost, and 2,002 steps if you do it outermost. And if it's not 1,000 but 1,000,000, the difference is even more dramatic. So yes, clearly there are examples where innermost is better than outermost. And why is this the case? Well, it's the case because something is duplicated. Because if you do this in this naive way, then here you duplicate this non-evaluated argument, and then the effect is that you have to evaluate both this and this, although this used to be the same argument. So outermost might evaluate the same sub-expression twice, or 3 times or 4 times if it is doubled or copied 3 times or 4 times. So might evaluate the same sub-expression twice if it is duplicated. And so what Haskell does is it tries to do outermost evaluation, but it tries to avoid this disadvantage. Yes?
What about link or reference evaluation, so that if I have doubled the expression and one expression is evaluated, I can also say the result of the other.
Okay, so the suggestion is, why don't we do this in a smart way, and we keep in mind whenever we duplicate an expression, we realize this by references, and if we evaluate one of these arguments, the other one is evaluated as well. And this is exactly what Haskell does. So this is exactly the solution that Haskell takes, because this avoids this drawback here, but at the same time has all the advantages of outermost evaluation. So this is exactly the solution. So what Haskell does, Haskell uses the so-called lazy evaluation. So it's not at all eager, but it's as lazy as possible. It tries to solve the problem with minimal work. And that means it tries to do it quickly. So it does lazy evaluation. And this means we do leftmost, outermost. But if expressions are duplicated during the evaluation, then Haskell keeps track of this. Yes?
I was wondering, wouldn't it be even easier and faster if Haskell wouldn't be forced to always use the same evaluation strategy? Because here we have the guarantee that there's no side effect, so we can just switch to innermost evaluation and just calculate this result and then use that. We don't need to use references or anything.
Well, the problem is if you let the programming language decide which evaluation strategy to take, and sometimes it takes outermost, sometimes it takes innermost, then it becomes unpredictable what the termination behavior of your program is. Because as we've just seen, the evaluation strategy influences the termination behavior and the efficiency. And the programmer wants to predict whether the program that he or she wrote is terminating or not. That should not be pure chance and depend on the compiler. So I don't really know. I mean, you can change evaluation strategies, but typically you only do this if you are sure that this does not influence the termination behavior. And for that reason, Haskell doesn't do this. So it really does leftmost, outermost evaluation, but it does this reference thing to increase efficiency. So it's leftmost, outermost, but if variables are duplicated in this way, where a variable of the left-hand side appears twice or several times on the right-hand side. But if variables are duplicated in these defining equations, then Haskell keeps track of this and realizes this via references, via pointers. Then Haskell keeps track of this and realizes it by references. So in that sense, Haskell tries to do the best of both worlds. Yes? Yes?
Does this also work if the sub-expression doesn't get generated in the same step? So at the same
Well, so the question is, does this also work if the sub-expression is not generated in the same step? Typically, no. So, I mean, it depends on how clever the compiler is. Since this only influences the efficiency, of course, everybody will be happy if the compiler does something even smarter than this, because this cannot harm. But there's no guarantee that the compiler will do that. So here you can be sure, and you can use this for your programming style to make your program more efficient. Whether the compiler is even smarter than that, well, it depends on how good your compiler is. OK, so this is the evaluation strategy. And this is, of course, something that the user has to know, because, well, you want to write programs that terminate. most likely, and you want to write programs that are as efficient as possible. Okay, so in particular, this means if you have this program 3 and this program non-term, then the expression 3 of non-term 0 terminates in Haskell. So the result of this is 3, and you get the result immediately. Okay, so let's continue. So in this section of the lecture, I want to tell you some basic things about declarations. And well, what we've seen up to now is what are type declarations and function declarations, and how does the evaluation in Haskell work. And now we will extend this concept of declarations step by step to introduce a few more features in Haskell. So we have this definition here. And now we will extend this by certain things to introduce more and more of Haskell. Okay, so up to now, our programs look pretty simple. They just look like this: square of x equals x times x. So that's, of course, a bit naive, because if you want to have equations where you have conditions, then this is difficult in this way. So how can you deal with conditions? So that's one. So you want to have conditional defining equations. So that's the next feature that we introduced: conditional defining equations. And how could one do this? Well, let's look at another example. And in this example, we introduce a new kind of type. Up to now, we had integers or booleans and functions between them and maybe lists of them. But you can also have Cartesian products in Haskell. So let's write a function maxi, which should take two integers and give you back the bigger of these two integers. And one way to do this is the following. It takes a tuple of integers. So a tuple of two integers and returns an integer. So this is the Haskell way of denoting the Cartesian product. So in mathematics, you would write this: int times int. In Haskell, you write this. So this is the tuple. This is the type of tuples of two components. And the first component has type int, and the second component also has type int. Now, that's the type declaration of maxi. What's the function declaration of maxi? So maxi takes arguments that look like this: x, y. And now, well, these are integers, and it should return the integer that is bigger. So now we need a condition. We have to test whether x is greater than y or y is greater than x. And in Haskell, you can do this by writing a vertical bar behind the argument. And now comes the condition. So if this condition is fulfilled, if x is greater or equal than y, then the result should be x. And otherwise, the result should be y. So this is new syntax that was not allowed up to now. So let's extend our grammar to allow these kinds of conditions. Let's do this online. Let's do this live. So what did I do here? What was not allowed? Up to now, right-hand sides had this form equals exp. And now I extended this because now I also allowed something like this. Instead of equals exp, now there's another possibility. I can write a conditional right-hand side. And I can even write several conditional right-hand sides. So a conditional right-hand side 1, conditional right-hand side 2, conditional right-hand side n. And what is a conditional right-hand side? A conditional right-hand side starts with a vertical bar, and then comes a Boolean expression, and the remainder is as before. Then there's a quality sign and the result of the function, which is another expression. So this corresponds exactly to this definition. We have a vertical bar, then a Boolean expression, for example, this here, x greater or equal y, then an equality sign, and then the expression, which is the result. And this otherwise here is a predefined function. This is a predefined function that always returns true. That always returns true. So instead of otherwise, you could also write true. That would do exactly the same thing, but this looks somehow nicer because this is the way how you would write it as a human as well, if you define a function by case analysis. And if you do things like this, there's no need to have a complete case analysis here. So, I mean, you could have the case x greater y, x equals y, and you have no otherwise case. That's also OK. I mean, Haskell does no check for completeness of these conditions. But if you then try to evaluate the function and none of these cases holds, then you get an error message and your program crashes. So, but you can write programs like this. There's no need to make the cases in any kind complete. And the cases are tested from top to bottom. So, I mean, if you just write the otherwise case always holds, because this is just the condition true. So Haskell checks this from top to bottom. It first tries to check, does this condition hold? And if yes, well, this equation is taken. And if no, it takes the next equation. So conditions do not have to be complete, and they are checked from top to bottom. Do not have to be complete, and they are checked from top to bottom. Okay, so we have now introduced the concept of conditional defining equations and also of the Cartesian product. Now let's get to the next concept. I mean, this is probably not too complicated. This is just syntax. The next concept is a bit, well, new if you haven't seen it before, because this is something that we only have in functional programming, but not in other programming languages, and that's the concept of currying. Now that's a strange name, and the reason for this name is that this is named after a well-known logician whose family name is Curry, and I guess most of you know what his first name was. No? Haskell, yes. So this is named after the logician Haskell B. Curry. So he was so important that his first name was used for the name of the programming language, and his last name was used for this technique. So what's currying? Well, to illustrate this, let's again look at an example. Let's define plus, so addition of numbers. So how can I do this? I could use, so let me write down the definition of plus. So plus is a function that takes two integers and adds them up. So if I use this notation with the Cartesian product, then the type would be the following. It takes two integers, so a tuple with two integers, and it returns an integer. And how is this defined? Well, it takes an x and a y, and it returns x plus y. So you could write it like this, but Haskell programmers don't like this. So they would never write something like this. Typically, they would write something else. So this is version 1. But instead, a Haskell programmer would rather write the following. The Haskell programmer would say, well, plus is not a function that takes a tuple of two integers. It's just a function that takes a single integer. And what does it return? Well, it returns a function that waits for another integer. And if you give this function this second integer, then the result is again an integer. So what does this mean? Now, plus is a function that takes a number and returns a function from int to int. Now, this is very confusing. How would the function declaration look like? It would look like this. Now, plus is a function that takes only an integer, just an x. So plus x is a function from int to int. If I give plus x an argument, some y, then the result should be x plus y. So what does this mean? The step from this version of the function to this version is called currying. And the step backwards from this version to this version is called uncurrying. So let's try to understand what this currying means. So now I can write something like this. I can write plus 2. Now plus 2, if I apply plus to an integer, then this is a function. So this thing has the type int to int. This is a function from integers to integers. And what does this function do? It waits for a number, and then it increases this number by 2. Let's try it out. If I apply this to a number, 3, then suddenly this left-hand side here matches. I mean, I have plus and plus here. If I instantiate x by 2, I have 2 here and 2 here. If I instantiate y by 3, I have 3 here, I have 3 here. So then this left-hand side, plus 2, 3, is here. So I can replace it by the corresponding right-hand side, which is x plus y, so 2 plus 3, which is 5. So plus 2 on its own is the function that increases numbers by 2. So I can now write something like plus 2, and this is the function that waits for an argument, for another argument y, and then it returns 2 plus y. That waits for an argument y, and if it gets this argument y, it returns 2 plus y. So typical Haskell programmers, they don't like functions that take several arguments, but they like curried functions. And the nice thing about these functions is that they get the arguments one after another. So instead of waiting for both arguments of plus, you can give it the first argument. And maybe later on the second argument comes, but you can already do this kind of partial application. You can apply a function of arity 2 to just one argument, and then this is again a function that waits for the missing argument. So the advantage is, what are the advantages of currying? So a function of arity 2 can already be applied to just one argument. And of course, in general, a function of arity n can be applied to m arguments if m is less or equal to n. Can already be applied to just one argument. So we have these partial applications. So this is one nice feature. And the other nice feature is that, well, I mean, Haskell programmers are lazy. I mean, Haskell has lazy evaluation, so Haskell programmers are also lazy. And they want to write as few brackets as possible. And in this way, you can save brackets. So you need less brackets. Why? Well, because if you write int, arrow, int, arrow, int, without any brackets, then Haskell associates this arrow to the right. So I can just write this, and this stands for int, arrow, int, arrow, int, brackets to the right. So this arrow associates to the right. So these brackets here are not necessary. I can remove them. And on the other hand, if I write something like plus 2, 3, then function application associates to the left. So this stands for first apply plus to 2, and then apply the result of this to 3. And in this way, this fits well together. So typically, the Haskell programmer would not write these brackets here. And then you can just treat this like a function with 2 arguments, but you omit all the brackets. And it is allowed to apply plus to just one argument. And then it's the function that waits for another argument and adds x to it. So plus 2 on its own is already a valid expression. And if one day it gets another argument, then the addition can really be performed. So this looks strange if you see it the first time, but it turns out to be very, very natural, and very soon you will be writing these kinds of functions as well without thinking about it. So to modify the grammar, we now allow the application of a function to not just one pattern, but to several patterns. So here this variable is applied not just to pattern 1, but to pattern 1, 2, 3, till we reach pattern n. And here you see how this looks like. So here this variable, this plus, is applied to one pattern and to the second pattern. And this you can do due to currying. OK, this needs some time to get used to. Yes? Is there a reason to perform uncurrying? Maybe if you want to make sure that partial application is not allowed. I mean, here there is no way to apply plus to just one argument on its own. It always has to be a tuple of two arguments. But that's so that there's no strong reason to perform uncurrying that I could think of at the moment. But yeah, it is possible. I mean, it's just that you know this name. So if you know currying, you should also know uncurrying. You can always undo it again if you're not happy with currying. OK, so before I show you the next extension, I have to wipe the board. OK, so now let's introduce the next concept. And the next concept is an extension where we have not just one function declaration, but several defining equations for the same function. And the idea is that we use several different defining equations for different forms of arguments. So for different forms of arguments described by patterns. And so this concept is called function definition by pattern matching. By pattern matching. So up to now, on the left-hand side of an equation, we essentially had just variables. So up there you can see we wrote something like plus of x, y. So x and y, they stood for the arguments that we expect here, and they are just variables, so they describe arbitrary arguments. Now in general, these patterns can look differently, and to give you an example, let's define a function for Boolean conjunction, so AND. But AND is predefined in Haskell, so I need a different name. So I call it und. So this gives the English-speaking people in the audience the opportunity to learn some German. So in case you didn't know, this is the German word for and it's pronounced und. So it's and goes from bool to bool to bool. So I use currying here already. So typically you would expect this to be a binary function, but now it's a unary function. It takes one Boolean value, and then it waits for another Boolean value, and if it has both these values, it can compute the result. So how does und work? Well, if the first argument is true, and the second argument is something arbitrary, a y, then what is the result? Y. Exactly. And if the first argument is false, and the second argument is some y, then what is the result? Y? No, false. Otherwise, this would be the projection in the second argument. So then the result is false. So what do we see here? Well, we suddenly have two function declarations for the same function symbol, this one and this one, but they have different arguments. So now we use another pattern. It's not just the pattern y for a variable, but we also have the pattern true and the pattern false. And they describe, well, true describes exactly the value true, false describes exactly the value false. So it's rather clear for which arguments we have to use this equation and for which arguments we have to use the other equation. So true and false are the so-called data constructors of the data type bool, of the type bool. And, well, data constructor means that every object of this data type can be constructed from these two functions. So these are the data constructors of type bool, and this means every object of this type bool can be constructed from these data constructors. Well, in this example, these are functions of arity 0, so there's not much to construct. Bool has exactly two objects, namely this one and this one. But I mean, bool is a very simple data structure, and for more complicated data structures, this is a bit more interesting. So every object of type bool can be constructed from the data constructors, from its data constructors. So in other words, so data constructors are functions like anything else, but the data constructors, they are not evaluated further. So if you have something like square or und, they are evaluated further. Haskell expects that there are some definitions for und and for square, so some defining equations. But true and false are not evaluated further. And to make this clear to Haskell, which functions have to be evaluated and which functions do not have to be evaluated, one writes them with different syntax. The data constructors start with capital symbols, and the other functions that have to be evaluated, they start with lowercase symbols. So data constructors, they start with capital symbols. So for that reason, we have capital T and capital F here. So they start with capital letters, and in contrast to the other functions, they are not evaluated further. There are no defining equations for them. So how does evaluation work now, since we have several defining equations for the same function symbol? So if we have an expression like this, to evaluate something like this, where we have und and then exp1, exp2, Haskell checks these defining equations from top to bottom. So check the equations of und from top to bottom and take the first one that matches. From top to bottom, and take the first one where the patterns match. And patterns, they are essentially terms or expressions built out of variables and data constructors. So this is more or less expressions built from variables and data constructors. From variables and data constructors. So if we look at that, then we can see, well, if we want to evaluate some expression where exp1 is true, then the first one will match. And if we want to evaluate something where exp1 is false, then the second one will match. And this shows us that we can simplify this a bit. There is no need to really check for false here. We could instead also write just x here. So if we write x here, it would work in the same way. If we now, so let's do this and let's see what happens. If I now write und of false true, what would happen? Well, Haskell would start checking whether this matches. And then it sees, OK, here we have und, there we have und, that's fine. But here we have true, and there we have false. So this doesn't match. And then Haskell tries the next defining equation. Here we have und, there we have und, here we have x, OK, there we have false. But x stands for anything, so x matches. Here we have y, there we have true, so y matches as well. So the second equation works, this matches, and so the result is false. So even if we write it like this, und will still evaluate correctly. So you look skeptical? No? OK. It will still evaluate correctly because equations are tested from top to bottom. Of course, if you change the order of the equations, then, well, the other equation would never trigger, and you would always get false. So the order of the equations is important. So to make this more interesting, let's define another function which I called unclear. And unclear takes an integer and returns a Boolean. And what does unclear do? Well, unclear does something unclear. it takes an integer, and then it calls itself with a not in front. So it's not of unclear x. So this looks rather non-terminating. I mean, unclear of 0 evaluates to not of unclear 0, which evaluates to not of unclear 0. It's very unclear whether this is true or false. The only thing that's clear is that this is non-terminating and rather strange. So to recapitulate how evaluation works in Haskell, let's evaluate und of false and unclear 0. Unclear 0. What's that? Yes? It's false. Because, well, Haskell starts checking here. This doesn't work. Here we have true, there we have false. These are different data constructors. So this equation is not useful. And this one is. X matches false, Y matches unclear 0. So we can replace it by the right-hand side, which is false. So this terminates and gives false. And what happens if we change the arguments? So und of unclear 0 and false. What do you think? It does not terminate. And why doesn't it terminate? Because it doesn't terminate because Haskell has to find out whether this equation is applicable. And to find this out, it has to find out whether this thing will start with this data constructor. If it can be sure that it's not true, then we can ignore this first defining equation and look at the second one. But Haskell doesn't know. Maybe unclear 0 evaluates to true. So Haskell will start evaluating this until it can find out whether it starts with true or not. So Haskell has to start evaluating unclear 0 until it knows whether the first equation will be applicable or not. Whether the first equation applies. And well, so Haskell will evaluate it one step, and then we have not of unclear 0 here. And then Haskell still doesn't know whether not of unclear 0 will be true or not. So it starts evaluating a second step, and then it still doesn't know whether it's true or not. And well, it continues like that. So it starts evaluating this, and it never finishes because it would only finish as soon as it knows that this will never be true, or this will be true. But Haskell can't find out, so this is non-terminating. So, yes?
Will something change if we will change the order of the operators and try to execute the same thing again? We will try to evaluate unclear 0 to x again?
You mean if I change these two equations?
Yes.
Or if I change these two equations, und will always return false. So if this would be my first equation, und of x, y equals false, then x would match unclear 0, y would match this. It would not evaluate this at all, because it only has to evaluate to find out whether the pattern matches this argument. And x matches anything. A variable matches anything, but this only matches the value true. And so that x matches unclear 0 is clear, but whether true matches this, Haskell doesn't know, and so it starts evaluating, and it will never find out. So it's not terminating. So this is something to get used to. To have what on the right-hand side?
Could we write true instead of y? So swap x and y.
Here.
No, on in the second argument.
Here. So you would like to have true, 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 false, and so on.
No, I'd like to have x true is equal to x and xy is equal to.
Okay. Let's write it down. So you want to have und of x true is equal to x, and of x false is equal to false. Something like this?
Yeah, something like that.
That seems to be correct, right? So this is conjunction, if we made no mistake. Well, it depends. I mean, if you now write something like unclear, whatever, sorry, not unclear, und. If you now write und of false and unclear 0, this also doesn't terminate because, I mean, x matches false, but whether true matches unclear 0 is unclear. So it makes no real difference.
And if we combine unclear 0 false, would that terminate in this case?
You want to write unclear 0 into the left-hand side of the equation? No. Yeah, OK, you want, but yeah, it's not allowed. So in the left-hand sides of the equations, in these patterns, you can only have data constructors and variables. And again, for good reason. So,
I don't mean the definition of the function.
OK.
I mean, when trying to execute that, I want to evaluate unclear 0 false with the definition on the left-hand side.
Oh, you want to have these two definitions, and Haskell picks the one that is most appropriate? No.
I can add to the definition above. I can add the line x false equals false, right?
Yes. And where? Here?
Yeah.
So und of x false equals false. Well, even if you do this, then this will still not terminate. Because Haskell will start with the first equation. And it first has to find out whether this matches. So what you would like is Haskell looks at all these equations and it takes the one that fits best. But that's dangerous because nobody prevents you from writing something like und xy equals true and und xy equals false. I mean, that's perfectly legal Haskell. The effect is that this is never used. This is always disregarded because Haskell takes the one that matches first. OK, maybe Haskell warns you, but Haskell would accept this. I mean, this is probably not good style, but
I'm actually not sure whether any, say, Haskell compiler will compile this.
maybe it will not compile this. But I mean, also here you have contradictions. I mean, with true and false, this evaluates to with true and true, this evaluates to true, but with true and true, this evaluates to false. So if Haskell were free to pick the equation it likes, then it's unpredictable what the result is. Because these defining equations, they don't have to exclude each other. And, well, that makes, for that reason, for good reason, Haskell executes this from top to bottom and cannot pick. So it first has to make sure, does the first equation match? And only if the first equation for sure doesn't match, it can take the second. OK. So we have pattern matching. And we've seen that pattern matching works for Booleans. But in fact, pattern matching works for any data type, not just for Booleans. So how does it work for other data types? So if we do pattern matching for Booleans, then we benefit from the fact that the data type bool is defined by the following grammar rule. If I want to have a Boolean value, well, then the value is either true or false. So if you want to define the concept of bools by a grammar rule, you could do it like this. Bool is either true or false. And pattern matching means essentially I do a case analysis corresponding to this grammar rule. And now, in a similar way, you can do this for other data types as well. Let's do it for lists. So how would pattern matching work for lists? So pattern matching for lists. So let's maybe do this first for lists of Booleans. So lists of Booleans, this data type. How do the objects of this data type look like? How can I construct lists of Booleans? Well, lists of Booleans are either the empty list, or it's a Boolean value inserted into a Boolean list. And in Haskell, this is the function symbol used for list insertion. So in this way, you can represent a list that has this first argument and this remainder list. And in fact, you can do this for lists of any type. So, well, this is how to do it for lists of Booleans. And if you want to do it for lists of any type A, the same thing would work. So if you want to construct a list of any type A, it's either the empty list or it's an element of type A inserted into a list of elements of type A. So, I mean, here we distinguished, we made a case analysis depending on whether an argument is true or false. And so here we can make a case analysis and distinguish whether the argument is the empty list or the non-empty list. So let's do this with an example. And, well, we had one example already. Let's compute the length of a list. So let's compute the length of a list. For example, a list of Booleans or a list of integers. Let's take a list of integers. And return an integer. So how would that work? We now do this case analysis. Either the first argument is the empty list or the first argument is a non-empty list. So something built with the data constructor colon. So then it looks like this, x and xs. So for lists, we have these two data constructors, the empty list and colon. These are the data constructors for lists. Are the data constructors for lists. And so we can have two function declarations for len which handle these two cases. And, well, the length of the empty list, what should the result be? It should be 0. And the length of a non-empty list, it should be 1 plus the length of x's. And, well, again, how does this work? If we apply len to an actual argument, we had this before. So if we apply this to a list like this, 15, 70, 36, then we have to keep in mind that this is just a syntactic sugar. It's just a nice looking short notation for the following term. This stands for the following term. It's 15 inserted into the list, where 70 is inserted into the list, where 36 is inserted into the empty list. So in reality, we have this term here. And this is just a nice looking way to write the same list. But Haskell converts this into this. And so now Haskell does the same thing. It does pattern matching, and it checks the equations from top to bottom. So it checks, does my argument start with this constructor? And it does not, because it starts with this constructor. And so this equation doesn't match, but this equation matches. And how does it match? Well, x has to be instantiated with 15, and x's has to be instantiated with this thing. And so this evaluates to 1 plus len of x's, and x's is this thing. So in nice looking notation, it's 70, 36, and in real notation, it's 70 inserted into 36, inserted into the empty list. And as I mentioned, Haskell programmers are lazy, so they try to avoid brackets whenever possible. And if you avoid the brackets here, it associates to the right. So these brackets are inserted automatically. And now, of course, this continues, and then after a while, we get 3.
Sorry?
Yes?
Would it be a performance improvement if we did the second check first to avoid having to check for an empty list if we're usually checking for a length of list that's not empty?
Yeah, OK. It could be a very minor performance increase because you do the, I mean, this check only will work once in the very end, and this check works in all the other cases. So yeah, you're right. But as far as asymptotic complexity is concerned, it makes no difference because, I mean, this thing is linear no matter whether you do it this way around or the other way around. So I guess it's negligible, but indeed, it could make an important. I mean, if you have a smart compiler, maybe it turns it around, but you don't know how smart a compiler is. OK, so what do we see? We see that patterns are composed of variables and data constructors again. So here we have terms consisting of variables and of colon and of the empty list. And of course, now we have a bit more interesting data constructors. And so we can also construct more patterns than just these. So for example, let's do this once more. let's write an algorithm that returns the second element of a list. So not the first one, but the second. And this can also be done by pattern matching. So how would we do this? So second should be an algorithm that takes a list, for example, a list of integers, and it returns an integer, and this should be the second element of this list. So this could look like this. Well, second of the empty list, this has no second element, so let's return 0. And second of a list like this, this also has no real second element, so let's also return 0. But second of a list like this, x colon y colon x's, now the second element is y. So what do we see here? We see that you can really write arbitrary terms consisting of variables and data constructors. So the patterns are really built from data constructors like colon and empty list and variables. And variables. And you can also use this nice short notation in the patterns. So instead of this, you could also write the list containing x. So maybe I should do this to make this more readable. So you can also write something like this here. This means the same thing. This is just a short notation for x colon empty list. It's a list containing just x and nothing else. Okay, so this is about function definition by pattern matching. And now for the next thing, again, I have to wipe the board. Yeah.
I'm a bit confused. When should we put a parentheses for a second? For example,
Yeah.
last time for a second you put a parentheses for those x, y axis. Is that necessary for anything?
So you mean these parentheses, why I put these parentheses. Yeah, OK. So the problem is that this colon is an infix operator, because you write the arguments of you write this colon between the two arguments of the function, whereas second is a prefix operator, so you write this before the argument. So if you write something like, so typically when you write something like this, f x colon x's, if you don't write any brackets, then Haskell means that most likely you want to apply the f to the x, and then this result should be inserted into the list x's. So this could be confused with this. So the question, is this, or is it this? Yeah, these are the two possibilities. And well, whenever this is not completely clear, it's better to write parentheses, and then you avoid any misunderstanding. So better try to avoid misunderstandings so that no misunderstandings occur. So here, second is applied to this list. So this colon applies to x, y, and x's, but not to the second. OK, so we have introduced the concept that you can declare functions, but of course you can also declare constants. So you can also declare functions with no arguments. And if you do that, you can even declare a bit more complicated things. You can declare whole patterns. So instead of function declarations, one also allows pattern declarations. And that's not something very complicated, but just to show you that this is allowed. So for example, I can write something like this. So this should be the number pi. Well, pi is predefined, so I added an n. So now it's pi new, the new pi. What is pi? Pi is a floating point number. And there are also predefined data types like float and double for floating point numbers in Haskell. And now I can write something like this. This should be the number 3.1415927 and so on. OK, this is just like we do the definition for functions, but now this is not a function, it's just a value. It's just a floating point number. So this is the particular form. This in particular is also a pattern because it's a variable. And variables essentially are terms built from variables and data constructors. So you can write something like this. You can also write something like this. So let's say x0 and y0 are both integers. And this is now also a pattern, x0, y0. This is the pattern standing for arbitrary terms of integers. But now we say this pattern x0, y0 should, for example, be 1, 2. And if we do this, then now we have declared that in the end, x0 is a constant standing for 1, and y0 is a constant standing for 2. And, well, we can also do declarations like this. We could also say x1 and y1 are both integers. And x1, comma, y1. This is the list. 1, 2. So this would also have the effect that this list is now considered to be this list. And this is, again, a pattern. It's a term built of data constructors and variables, because this is just a shorthand for x1 colon y1 colon empty list. So this term is 1, 2. And so any form of, you can always declare that some pattern should be some fixed expression as long as it's clear which value each variable in this pattern gets. So here x1 gets the value 1 and y1 gets the value 2. And so what is your solution? X1 should get the value 1 and 2?
Yes, it's a list, and if like y is getting an empty list.
I mean, you mean, oh, x1 should be the list 1, 2?
Yes, and y1 is getting an empty list.
And y1 would be the empty list. Well, there are several reasons why this is not possible. One reason is that x1 and y1 are both integers, according to this type declaration. And moreover, if x1 were this list and y1 were this list, then what would x1, comma y1 be? It would be a list of lists. The first list in here would be 1, 2, and the second list would be the empty list. And this is not the same as this list. So this is a list of integers, and this is a list of integers. Okay, one more example to recapitulate currying. So I can also write something like this. I can write suc. Now suc is a function from int to int, but in fact suc is just a variable which stands on this left-hand side, and it's defined to be +1. And plus we defined as before. So plus was the function from int to int to int, where plus of xy is x plus y. So now you can, this is again an example for partial applications, because plus is now only applied to a single argument. And so suc is the function that is like +1, but it waits for another argument, and when this other argument comes, it increases the argument by 1. Let's evaluate this. So let's say I want to compute suc of 3. So what does Haskell do? Haskell does outermost evaluation. It looks at the outermost expression that it can evaluate. So it sees, aha, suc, I can evaluate. How do I do it? I can replace suc by +1. So let's do it. Then I have +1, 3. And now Haskell sees, aha, I can evaluate this plus, because plus xy can be evaluated to x plus y, and plus xy matches this thing here. So this can be evaluated to 1 plus 3. Plus is predefined, so the result is 4. So this is really, this currying really fits nicely with the rest. It's just pattern matching and evaluation and replacing left-hand sides by right-hand sides. So this really works as expected. So to extend this to pattern declarations, we have to introduce another possibility. In addition to function declarations, now we also allow pattern declarations, so pat decl. And what is a pattern declaration? A pattern declaration. It's just on the left-hand side we have a pattern. So an expression built from data constructors and variables. And then we have equality sign and an expression on the right-hand side. So a right-hand side of a function declaration as before. So the only difference is that now on the left-hand side we have just this pattern and not the name of the function and the arguments, but just a single argument, which can be an arbitrary pattern. And now let's move on to the last concept that I want to introduce to you today. And the last concept are local declarations. So what are local declarations? Local declarations are declarations which are not on the top level of the program, but which are only specific in one function declaration. So you have a function declaration, and in that declaration you introduce a sub-declaration which is only in effect for this single function declaration and not for the whole program. To illustrate this, let's look at an example. Let's try to solve quadratic equations. So our goal is we have a quadratic equation like this. Ax squared plus bx plus c equals 0, where a, b, c are rational numbers. And the question is, what are the values for x such that this equation holds? Now in high school you learned how to solve this. This holds if and only if x is the following. It's minus b plus minus square root of b squared minus 4ac divided by 2a. So I hope this looks familiar to you. And depending on whether this is negative or 0, you have two solutions, one solution or no solution in the real numbers. OK, so let's write a Haskell program which computes this. I call this roots because it has to compute the roots of this polynomial here. So those values for x where this polynomial becomes 0. So roots takes as input the value of a, the value of b, and the value of c. And as a result, it gives me the possibly two roots of this polynomial. So it gives, let's say these are all floats. So this is the value for a, for b, and for c. And since there can be two solutions, the result is a pair of the two solutions, well, depending on whether I take plus or minus here. And what is the function declaration? Roots a, b, c. Well, of course, I could now copy this whole definition in Haskell, but the problem is that this thing is complicated to compute. I mean, I have to compute b squared, and I have to compute the subtraction, and in particular, I have to compute the square root, so this is rather ugly. So it would be better to compute this thing only once, let's call this d, and this thing only once, let's call this e, and then I store this result. I mean, if you do this in imperative programming, that's how you would do it. You would compute this first, you would compute this first, give it a name, and then, you would compute the first solution, minus b plus d divided by e, and the second one, minus b minus d divided by e. So let's do this here as well. So we compute minus b minus d divided by e, and the second solution is minus b plus d divided by e. But now, of course, Haskell doesn't know what d and e are. And for this, we add a local declaration. We say, well, d is this thing. So it's square root of b times b minus 4ac. And what is e? E is 2 times a. And something like this is called a local declaration. So here we have added 2 more declarations. This is a pattern declaration. We declare the pattern D. So D is a constant. It's just this thing here. And E is a constant. It's just this thing. But this D and E, they are only visible in this right-hand side. So in the next defining equation, D and E are no longer known. They are only known in this right-hand side. So this where keyword tells us that now comes a local declaration which is only accessible in this right-hand side and nowhere else. So this thing here is a local declaration. And the advantage of these local declarations is, in particular, that we have, well, if we do it like this, the advantage is that this is more efficient than computing this expression twice. Because now this square root thing is computed once, and then it is used here and here. So we don't have to compute it twice, but only once. And similarly for this 2 times a thing. So, sorry?
Wouldn't the linked evaluation work here as well?
The linked evaluation? No, it would not work. So if you have this, if you would copy this square root expression here and here, it would not be a duplication of variables from the left-hand side to the right-hand side. So, I mean, if your compiler is very smart, it might notice, but otherwise it would not notice, and then it would really compute this twice. Whereas here, it will only compute it once. I mean, you can try it out with something more complicated and then see how long it takes. Yes?
What happens if D is not a rational number?
Yeah, if D is not a rational number, you get some exception, I guess, because then you take the square root of a negative number. I mean, yes. Okay, to do this in a smart way, you would have to check this first. But that was not the point. I mean, I want to make the code as simple as possible. And of course, this is in no way robust. Because, yeah, if this, I mean, this will not deal with complex numbers because D is designed to be float. And, yeah. Okay, yeah, this will crash if this is a negative number. Okay, so what is the advantage? So the advantage is that the expression in D and E is only computed once. Is only computed once. So what we can do now is we can extend the definition, we can extend the syntax of Haskell declarations. We have to do this anyway because this is no longer readable. Oh, this looks very fancy. Okay, so how do we extend it? Well, we extend it by these where clauses. So now suddenly, for every function declaration, we can add such a where clause in the end. And these square brackets in the grammar indicate that this can be there, but it doesn't need to be there. So this is not mandatory, but, well, you can have it, but you don't need to have it. And if you have this where clause, then after the where clause comes a sequence of declarations. And decals means that you have a curly bracket, an opening and a closing curly bracket, and inside you have many declarations separated by semicolon. And these declarations, they are only visible in this right-hand side. So outside this right-hand side, they are no longer there. So they are really local to this right-hand side. And you can have this in function declarations and in pattern declarations. OK, and well, of course, Haskell programmers don't like curly brackets and semicolons. And how to get rid of that? Now, this is really strange. How to get rid of this, I will show you on Wednesday. OK, so see you again on Wednesday. There's no exercise course, but lecture. And I'll show you how to get rid of this.